one chapter, in my opinion. Chapter 8 brings in the mole concept. And then what we do in chapter 9 is take that mole concept and the equation concept that we spent so much time on and just tie them all together to make one big happy problem-solving mess. Okay? All of this is rooted back on that unit analysis or dimensional analysis method that we talked about way back at the beginning of the semester. So we designed the class to kind of throw a whole bunch of math at you, make you panic, freak out, then give you a break to kind of breathe a little bit, and then go right back into the math again. Okay? So we need to deal with this unit conversion system. If you move into 151 and 152, 90% of those classes is unit conversion. Okay? Yeah, it's super exciting stuff. Okay? But once you pick up that pattern of realizing it's just unit conversion, it becomes a little bit easier to process. Okay? So let's start it off real easy. What is the mass in micrograms of a 325 milligram aspirin tablet? If you've got really good notes, this answer should be easy. Why? How do we go through and deal with this? Yeah, one of those words. So our overall idea is to convert the milligrams to grams. That's fine, but think back to our dimensional analysis. What we want to start with is our answer. What do we want for an answer? We want micrograms. What do we start with? We started with, fair enough, milligrams. Do we know how many milligrams we started with? Now we can drop in our number. Okay? So before we do any conversions, is milligrams the same thing as micrograms? No. Okay, so we have to do a conversion. Okay, milligrams does not show up in the answer, so where should milligrams show up in my conversion? On the bottom. Why on the bottom? So that the units can cancel. Ideally, I want this to convert into micrograms. I personally do not know this. If this is something that you've memorized, that is on you to memorize. Okay? And if you do it right, good job for you. If you do it wrong, I'll give you a hard time for it. So I don't know how to convert it into micrograms, so I got to convert it into something else. Okay? So what I will convert it into will be grams. Mainly because that's the only thing I know how to convert it into. Okay? So I really don't have any choices. That's the only option. Okay? What numbers need to show up in front of that? So this comes back to how we decided to set up our conversions. There is 1 milligram, and the milli stood for 10 to the negative 3. So our power of 10 will always affect the base unit. For those of you that memorized the 1,000, you are doing something slightly different as far as your numbers, mathematically exactly the same. Right? As long as you put the 1,000 in the denominator, not the numerator. My units convert across, and I now have a new question. My new question is, grams need to be micrograms. Are those the same? No. So I need to do yet another conversion. In that conversion, I need to think about what units I want and what units I don't want. Well, I don't want grams in my answer. What do I want? Micrograms. Do I know a conversion between grams and micrograms? Yeah, that was given to us up at the front. We know 1 microgram is 10 to the negative 6 grams. I can now punch it into my calculator and I get a really big number. We should get 325, what was that, million? We already had this conversation. That's 1,000, yeah. 325,000. Okay? Questions? This is the format we must follow for every single conversion we go through and do. Okay? What we'll find in Chapter 8 is we're going to introduce a couple new conversion factors. Those conversion factors are the same thing that we've got in here. That is a conversion factor. That is a conversion factor. Okay? That's all we're trying to do. New conversion factor, allowing me to convert from one unit to another. Okay? Questions? Okay. So we talked about this, okay, or briefly. This is kind of our birth of moles. So what we've got there is a Lego Hogwarts. So this lady decided to build Hogwarts out of Legos. Okay. How many Lego bricks went into that? Okay. We could go through and count every single one of those, or we could start to group them as units. We could say there's 7 dozen, okay, as opposed to saying 7 times 12, 84. Okay, as opposed to saying 84. So we can invent new units to allow us to explain the massive amount of Legos that went into that. Where this becomes relevant is that when we move to chemistry, we're looking at atoms. And we're using atoms as our Legos to build larger things. Well, in those larger things, we've got lots and lots of these individual atoms. Okay, so it becomes way too difficult to count the number of each of the atoms. Instead, what we end up using is this concept known as a mole, which is just a really large number of those. Okay? So our chemistry gives us a rule set. So our formulas gave us the atoms used to build a molecule. Our equations gave us molecules to build new molecules. So both of those things give us a conversion factor. Formulas allow us to see how many atoms we need in a molecule. Equations allow us to convert one molecule into another molecule. Okay? And because we're looking at atoms and molecules and they're so tiny, we invent a new scale on our system. That's the whole point of moles. Okay? So what is a mole? Well, before we even get into that, a farmer has 72 chickens. Each chicken lays 2 eggs per day. How many eggs can the farmer collect per day? A couple. Okay. So what could we go through to do to solve this question? What do we want as our answer? We want eggs.
12.
Officially, we don't want just eggs. What do we want? We want eggs per day. What information are we given? We know we have 72 chickens. Okay. And we know that each chicken lays 2 eggs per day. So one chicken, how do you spell chicken? I've been having a really hard time spelling today. Okay. So we've got one chicken gives us 2 eggs. Man.
We forgive you.
2 eggs per day. What happens? The chickens cancel, and we'd end up with, yes, it's a slash. Eggs per day is our unit. Okay. Do we have to write it this way? No. One of the things that we can do using our mathematical terms is we can actually do this. Same deal, exact same relationship. So mathematically, we just do 72 times 2, and we end up with 144, which everybody shouted out as an answer. Great for you. Good job. Okay, you can do that math. I don't care about the math. I care about the units behind the math. Okay. The next part of this that makes this a little bit more challenging. Let's see if I actually put this on as a slide addition. Okay. Our farmer cannot understand numbers larger than 10. So you come in and tell him he's got 144 or larger than 15 or 20. Okay, let's stick with 20. Okay, 5 fingers, 10 fingers, 5 fingers per hand. And it's recording, even better. 5 fingers on each hand. 5 fingers on each foot. We can only count up to 20 things. That's as far as the farmer can count. If you come in and tell him he's got 144 eggs per day, he doesn't understand that, he's going to have a hard time comprehending what that means, because all he can understand is 20. 144 doesn't work. Okay? So how can you change that result so that the farmer can now understand that? Okay? Instead of looking at this as 144 eggs, you can go through and explain to the farmer that 12 eggs equals 1 dozen. Well, he understands what 12 is because that's less than 20. We can deal with that. And he now knows what a dozen is. Okay? So what we can then do is change that 144 eggs per day to now becoming 12 eggs is 1 dozen, and our answer becomes 12 dozen eggs in a day. Now he's okay with it, understands everything you're talking about. Okay. I'm not trying to pick on farmers, but farmers have eggs and chickens, so it makes sense on them. Okay. And farmers can probably understand the 144 egg issue as well. Okay. That's not what we're getting at. What we're getting at is that when we move to chemistry, we're not looking at 12 anymore. Okay. We're looking at a massive number of atoms. That number gets so massive that we just can't physically comprehend it. So we converted it into something else for us to understand. Okay? And that's a mole. Okay, so we're going to write that number up here. 1 mole, just like 1 dozen, okay, is now 6.022 times 10 to the 23rd. Let's go ahead and stick with eggs. Okay, whoops. 1 mole of eggs, get the stupid eraser to start working, is 6.022 times 10 to the 23rd eggs. Okay, that's a lot of eggs. Okay. But that's what's happening in our scale of chemistry. What we're working with to run an individual reaction is that many atoms or that many molecules to deal with a scale that's reasonable for us to measure. That's a lot. Okay. And if we dealt with a chemical reaction where instead of saying A plus B goes to AB, we now had to write in here 6.022 times 10 to the 23rd of those plus 6.022 times 10 to the 23rd of those gives me 6.022 times 10 to the 23rd of those. We get really tired and sick of writing that number out. Okay. So what we've invented, which it really is, it's an invention. It's as much an invention as saying a dozen. It's just a way of changing the massive scale of that number down to something that we can kind of comprehend. Okay. The reason behind why we picked that number has a whole bunch of other side effects that are really cool that allow us to do a bunch of other chemistry swiftly and easily, use periodic table, all of that fun stuff that we've already been doing. Okay. So that's one of the reasons why we picked that number to represent a mole. Okay. But at this point, all we need to know is that number is a mole. Okay. What can we do with this? Well, we just started to look at a reaction. Okay. We've got a bicycle here. What do we need to do to make that bicycle? Okay, paddles is a little too in-depth. Okay, well, we need some wheels. That's a wheel. Okay, we need a frame. Little handles, little seat there. Pretty good artist, right? It's a little small scale, but you know. Right, would that work? Can I build a bicycle now? I need 2 wheels.
That's why it's called a bicycle.
Good call. That's why it's called a bicycle. 2 for wheels, 2 cycles. Right? So this is a nice, simple overall reaction for explaining this. But what if I want to build 50 billion bicycles? How many wheels do I need? I need 100 billion. How'd you do that? Why'd you double it? Okay. What we end up doing in that conversion is if I need, what do we say, 100 billion bicycles, bikes, right? Whoops, other way around. I want to know how many wheels I need if I start with 100 billion, 50 billion, wasn't it? 50 billion bicycles. Right? You just multiplied by 2. I challenge you that you didn't just multiply by 2. Right? What did you do? You said bikes as a unit needs to cancel, and I need wheels as a unit needing to appear. How many wheels do I need per bicycle? 2 to 1. How do I know that? That's what this equation tells you. You're using that conversion factor out of that equation. And we end up with that 100 billion wheels. necessary to build a mound. Okay? Well, we pick numbers that are relatively simple to comprehend. But if our numbers have a bunch of decimals and all sorts of other values in it, that becomes a lot more difficult to understand. So what we have to do is understand the methodology behind it and let the units determine our calculation for us. So that we aren't just looking at the number, we're looking at the units. And our units tell us what the number is. They show us the method to get that calculation. They show us what to punch into the calculator. Okay? Questions? Okay, so let's try another one. How many molecules of CO2 are necessary to make 2 molecules of sodium hydrogen carbonate? What was that? What do we need to do to solve this question? Take a look. What do we want as an answer? Molecules of CO2, which I'll abbreviate MLCS. I'm lazy. What are we starting with?
Sodium carbonate.
We are starting with molecules of sodium hydrogen carbonate. Okay, how many of them? How many? 2 molecules of sodium hydrogen carbonate. We look at our question or our equation and say, okay, well, are those units the same? No, so we need to do a unit conversion. I need to get rid of molecules of sodium hydrogen carbonate, and I need molecules of CO2. What numbers need to show up in front of each of those? Where do I get that information? We need the balanced equation. Think back to the bike example. Why do we put 2 in front of tires or wheels and 1 in front of bicycles? How many wheels did you need to make a bicycle? 2 from a balanced equation. So what do we need to do? We need to go to our equation and use the numbers out of our equation. But before we start grabbing those numbers, what do we have to make sure is true? That the equation is true, that the equation is balanced. Is the equation balanced? No. So we have to balance it. What do we need to do to balance it? Okay. So you should go through that whole balancing process and notice that we need to put a 2 in front of the sodium hydrogen carbonate. Okay. Now our equation should be balanced. Okay. Now that our equation's balanced, what do we need to do? We go back to our question. We need to convert molecules of sodium hydrogen carbonate into molecules of CO2. What number needs to show up in front of those? What number shows up in front of sodium hydrogen carbonate in the equation? Guess what number shows up in front of it in the calculation? Oh, that's a stretch. Okay. What number shows up in front of CO2? What number needs to show up? Oh, yeah, I already answered that. Let's try that again. We get 1. Now we run through and do the calculation. How many molecules of CO2 are necessary? 1. The units solve the math. They tell us where to put the numbers. Anytime you jump to just punching in numbers, you run the possibility of putting those numbers in incorrectly. This is why when we talked about dimensional analysis, we talked about the method behind it. I don't care that you get the right number when you're doing a simple conversion where you're just shifting a decimal place. Because this is not shifting a decimal place. This is following the same dimensional analysis pattern that we've been using since day 1. What you now need to do is add that extra layer of interpretation on putting those numbers into the equation. Okay. Questions on this? Okay. What is the mass of 2 molecules of CO2? Anybody? Any ideas? Where'd you get 40 from? So you looked at the periodic table, you said carbon was 12, you said oxygen was 16, there's 2 of them, and we get? thought it was 40. No, it's a nice whole number. 16 times 2 is... No, you're right. Yeah. I can't spell, I can't add. This is a horrible day. We get 44. All right. 44 what?
Atom thing, atom mass.
Not there. Atom mass U. We get 44 AMUs. Well, we go into the balance, we can just change the unit over to AMU, right? Everybody's done that in the lab? Just change the unit across AMUs. Anybody done that? I would suggest you have a hard time of doing that. Okay. Why might I say you have a hard time of doing that? AMUs are kind of tiny. Okay. So it's atomic mass unit. It's effectively a standard way of adding your protons and neutrons. So it's the mass of every single proton and the mass of every single neutron in each of those atoms. And we added it up and we get that 44 AMUs. Okay. Let's convert that into a mass amount that we know, or a unit that we know. Anybody know? Give me a good unit that you use a lot. Moles is not a mass. Grams. How do we convert AMUs into grams? So number one, what do we need to do? Conversion factor. In that conversion factor, what needs to show up in it? Gram on top, AMU on the bottom. Nice fun panic moment. Anybody know what that is?
27
You don't have the number for me, though? 1 point, did you have it? No, it's not Avogadro's number. Oops. Put it in the wrong spot. I think it's 1.16 times 10 to the negative 24th grams is 1 AMU. I don't have it memorized either. Okay. Actually,
Is it in the book?
667, I think. It should be in the book. Okay, so we go through and we run that calculation. What are we going to get for our gram amount? Some number times 10 to the minus 24. Really big number, really small number? 6605. Really? 1.661. I was close. Okay. That gets us a wicked small number. That number is so small that there's no way we could feasibly measure that out. Okay. Just impossible for us to do. Okay. There's a nice little approximation. Your balances measure out to 0, 0, 1, right? They give you 10 to the minus 3. 2 molecules of CO2 is 10 to the minus 24. Okay. That's a couple orders of magnitude difference, right? Just a few. Okay, so we can't do that easy measurement. So what we had to do is take this information that our balanced equation gives us. It gives us a relationship between all of those molecules and allows us to convert from one substance to another. And we have to invent some kind of unit that gets the number of molecules and our mass relationship up to something that we can measure in the lab. That is where our mole concept comes from. Okay? To get our atomic mass, what we can do is pull our periodic table. We can look at the numbers underneath each of those. So for that example, we had CO2. We could look at the 16, and we could look at the 12. Right? We could get our atomic mass from that. What is the molar mass? So now molar mass is relating mass to moles. Our atomic mass measured the mass to atoms. So the units on our atomic mass was AMU, which is the mass per atom. What is our mass going to be for molar mass? Someone got it? Not quite. Moles is not a mass, though. It's our grams per mole. Well, if our atomic mass for carbon we said was 12 AMUs. To come up with a molar mass, that could be a bit dicey. Except someone spent the time, did the calculations, and found and picked a mole value that then gave us a molar mass to be
6.022 times 10 to the 23.
exactly the same as the atomic mass. Okay. So they picked a single numerical value to represent a mole that then allowed the atomic mass value that we pull off the periodic table to be the exact same as the molar mass. Why does this become important? Atomic mass values we can't do jack with. Molar mass values we can do something with, because that gives us a number of grams that we can use. So if I now ask for the molar mass of lithium, I can look at the periodic table and say it's 6.94. So if I want to know the mass of 1 mole of lithium atoms, what do? Heard it there? I want the mass in grams of lithium for 1 mole of lithium. Are those units the same? No, so we need a unit conversion or a conversion factor. What's our conversion factor need to be? Moles need to go on the bottom. What needs to show up on top? Grams. These would be grams of lithium and moles of lithium. What numbers show up on these? Our periodic table, the number for our atomic mass is now our molar mass. Lithium says it is 6.94. That is 6.94 grams per mole. What shows up in front of grams? 6.94. What shows up in front of moles? 1. If I want 1 mole of lithium, what is it? 6.94 grams. I now have something that I can measure out. Okay? I've got a number that reaches something relevant on my balances. Okay? So the mole value we picked gives us that useful information. It doesn't remove the information from the periodic table on our atomic mass. It actually just gives us another way to interpret that number. Okay? And that interpretation is massively important. Okay? So we could go through and look at the AMUs. We could look at the grams. You'll notice that I've got the gram to AMU conversion in the bottom now. Okay? So if we're going to measure out a mass, we can't measure out something that small. Okay? So we measure out a much larger amount, and that's where we get into a mole. So 1 mole is this value that allows us to get to a number of atoms that chemically or physically allows us to measure. This is that conversion, 1 mole to atoms. Does it have to be atoms? Because officially, this isn't just 1 mole equals 6.02. Really what we're saying here is that this is 1 mole of atoms equals 6.022 times 10 to the 23rd atoms. Do I have to measure atoms? Whoa, that wasn't supposed to happen. What if I measured eggs? What's 1 mole of eggs? 6.022 times 10 to the 23rd. Eggs. What's 6.022 times 10 to the 23rd molecules of water? That is 1 mole. Man, that stupid eraser. Of water. So what we're looking at is counting these things. I could theoretically use the unit of mass. If I wanted to know 1 mole of grams, okay, well, 1 mole of grams is going to be 6.022 times 10 to the 23rd individual gram units. That's a pretty useless conversion. Okay? That doesn't bring mass into this calculation at all. The unit is still moles. Okay? It's the number of units. Okay? When we look at eggs, we don't say 12 dozen eggs is 5 grams of eggs. Okay? We're looking at the number of those things. So it's looking at a physical piece, okay? Not a mass, not quality. Okay, it's a quantity. So how many moles of aluminum are in 3.42 times 10 to the 21st atoms of aluminum? Killing me on the math. Show up your units. What do we want as an answer?
Moles of aluminum.
What are we starting with?
Whatever that is.
I will accept atoms of aluminum. And we've got that number, 3.42 times 10 to the 21st atoms of aluminum. Are atoms of aluminum the same thing as moles of aluminum? No, so we have to do a conversion. What unit needs to show up in the bottom? Why atoms?
Because that's where it counts.
I need those units to cancel. What unit do I want to show up top? Unofficially, it's moles of atoms of aluminum. Okay, or moles of aluminum. It's supposed to be the same thing. What numbers need to go into that? 1 mole of atoms is 6.022 times 10 to the 23rd atoms of aluminum. What ends up happening? You were correct. You just need to divide them. The reason why the division thing that I will dispute a lot is that it is very easy to accidentally swap that. If you draw out and provide your units, there is no accidental swapping because your units show you how they cancel. Okay? So it's not just a division, you're actually showing that you need to do that. Okay? Questions on that? Ready to make it more difficult? No? Well, sorry, you don't get much of a choice. How many oxygen atoms are in 0.240 moles of O2? For this one a little bit. So let's start this off. What do we want for our answer? It says oxygen atoms. What is the formula for an oxygen atom? An oxygen atom is just O. O2 happens to be an oxygen molecule. We have to be careful with the units and what we're being asked to calculate. Okay? So we'll address that in a second. What do we start with? Keep going. It's not moles. Moles of O2. As you'll notice, or as I noticed as I walked around, I noticed everybody writing a number first in the unit. You'll notice, how am I writing it? Unit, then number. The units will tell you where the numbers belong. Numbers will screw you up every single time. What number needs to show up in front of moles of O2? 0.24. Stupid sig figs. 0. Yes, we should be aware of it, though it probably won't show up on the exam. But you should be tracking that. So we go through and we take a look. Moles of O2, what do we want as a final answer? We want atoms of oxygen. Is that a direct conversion? Okay. Moles of O2 is the number of molecules of O2. The number of atoms of oxygen would be counting all of the oxygens within each of those. We're looking at two different unit systems here, so we're going to have to be careful with this. This is not a direct conversion across. What we can convert that to, or now what we can think about, is potentially converting those moles of O2 into molecules of O2. Why is it not atoms? Is O2 a molecule? Yes. Is it an atom? No. So when we're looking at a mole of O2, we're looking at a mole of O2 molecules. So we have to be careful with our calculation and what's being asked of us. What is the conversion between molecules of O2 and moles of O2 molecules? 6.022 times 10 to the 23rd. I want a unit. Molecules of O2. It's a good thing I left myself lots of space. Times 10 to the 23rd molecules of O2 is equal to 1 mole of O2. So what unit am I now in? Molecules of O2. Is that the same thing as oxygen atoms? No. So I now need molecules of O2 to cancel with atoms of O. What is the conversion factor between the atoms of oxygen and a molecule of O2? How do you know there's 2 oxygens in 1 molecule of O2? I want a little bit more than it says there's 2. The formula subscript of 2 applies to whatever's directly in front of it. That formula for O2 says there are 2 oxygen atoms in the molecule of O2. Okay. Yeah, I wouldn't quite accept memorized, but now we can punch it into the calculator and we get our answer. Okay. So being very specific with the units that you're using will solve the question. What if I'd asked for how many oxygen molecules are in 0.240 moles of oxygen? Well, then we don't need to do this last calculation because I'm asking for oxygen. Okay? Only when I explicitly ask for atoms do I need to be worried about looking explicitly at the atoms of oxygen in the formula. Okay? Yes?
I'm just confused how the mole calculation goes into atoms, but you said it's molecules.
Remember what we said. It does not go into atoms necessarily. So this is one of the things that I attempted to fix up here. This was 1 mole of atoms. Come on. Equals 6.022 times 10 to the 23rd atoms. What was the other example we used?
Eggs.
Eggs. So I can go through and remove those. And I can write eggs because eggs is just a physical quantity, just like atoms. Did it have to be eggs?
To be bacon.
Okay. 1 mole, well, we got to be a little bit careful there. Bacon slices.
What I would do for that many bacon slices.
I think you'd be dead.
But you would die.
But you'd die with a smile on your face, so it's okay. Bacon slices. It could just as easily be, as I keep erasing more and more out of this, mole of molecules is 6.022 times 10 to the 23rd molecules. It is just a unit, 1 piece. Okay? So that can be an atom. That can also just as easily be a molecule, because all a molecule is a collection of atoms. It's a new piece. So what we're doing is just counting a new thing out. Okay? Other questions?
What if it was O3?
What if, okay, let's switch that up again. How many oxygen atoms are in 0.240 moles of O3? What's the name for O3? That was just kind of a long shot, so good job on you for getting that. It's ozone. How many oxygen atoms are in ozone? What would we have to change with our units? Every place that was O2 needs to become, that was not what I meant to use, but it works, O3. Now what else would we need to check? Is that conversion correct? No. That needs to become 3 oxygen atoms in 1 mole or 1 molecule of ozone. Okay. So we're using a mole conversion, which is just changing the number of them. Okay. And we're using an amount conversion out of our formula. So the atoms to molecules comes out of our formula. The molecules to moles comes out of Avogadro's number. Okay? Is that clock really right? Holy cow. So, does that mean if we measure a mole of a substance, it all comes out the same? It comes out with the same number of them, but are we going to get the same amount? Depends how we measure an amount. If we measure an amount as grams, no. Why not? Why would 1 mole of carbon give you a different mass than 1 mole of uranium?
The density.
It's not even the density. What changes as we go from carbon to uranium? The number of protons, the number of neutrons, and all of those contribute mass. Right? So as we move to different substances, we'll get different masses, we'll get different volumes because the densities aren't the same. Right? Lots of stuff will end up changing, but the number of those atoms will remain constant. And that becomes important because when we look at a balanced equation, an equation tells us what? We go back to the bicycle example. If I give you 2 bicycle tires, how many bicycles can you theoretically make?
1.
If I give you 100 grams of bicycle tires,
How big are pictures?
okay? You have no idea unless you know how much a bicycle tire ends up weighing. The balanced equation doesn't tell you mass, it tells you the number of them. Okay? It tells you effectively moles. Okay. So Avogadro's number, we can go through and do a whole bunch of these things and look at all sorts of fun relationships. So we can see that we have a relationship between our molar mass, and our atomic mass on the periodic table. So we could convert atomic mass units over into grams per mole. It's a really exciting calculation, which is going to be kind of boring. You end up finding out that the mass of 1 mole of carbon atoms happens to be 12 grams. Okay. Whereas if I had looked at the mass of 1 atom of carbon, it would have been 12 atomic mass units. Okay. Those relationships fall directly out of Avogadro's number. How often do you deal with the number of particles or the number of atoms in any kind of overall calculation? How often do you deal with a mass that's on the order of 10 to the minus 3? Sorry, not 10 to the minus 3. Let's try that again. 10 to the minus 23. Rarely. How about 10 to the minus 15? Okay. Very, very rarely. Are atomic mass units a useful unit? No. We'll never measure them. What we'll end up using instead is grams per mole. So while there is a nifty little relationship between Avogadro's number and looking at the mass, an atomic mass number for an element, and the grams for a mole of that element, that's about it. So when it comes to conversions, what we'll end up dealing with is grams and moles. That's it. All of our work is going to center on that. Because when we go into the lab, we have a balance that measures grams. So we don't want to use any other unit. That's our mass unit. Okay? So the atomic mass on your periodic table is one and the same as the molar mass. Okay? All we're doing is changing the unit. Your atomic mass for carbon is 12 AMUs. The molar mass for carbon is 12 grams per mole. Okay? The only unit you'll be really concerned about is your grams per mole value.
Is it like that for most of them?
Let's switch that around. Is it like that for most of them? Is it like that for every single element on the periodic table? Yeah. It's exactly true for every single element. Okay? That's the power of the periodic table. So if I asked for the molar mass of, let's avoid carbon. Let's say, here we go, let's just do water. Nice and simple. What's the molar mass for water?
18.
We take the mass of oxygen, which is 16 grams per mole. We take the mass of hydrogen, which is 1 gram per mole. But there are 2 hydrogens. And I add that up and I get 18 grams. Oh, man. Yeah, you can bring in your sig figs. You're right. Okay. Okay, and we can end up with our molar mass. So the periodic table gives us that value. And that's where we'll be sitting most of our calculations. Okay? So, conversion factors and where to find them. Okay? Individual measurements. Okay? We have metric measurements, milligrams to centigrams to decigrams to kilograms. I always say kilograms. Right? All of those you are required to have memorized. That was part of the thing that we talked about in the beginning. Officially, you need to know all of them, right? But you won't be tested all of them. Okay? The English conversions will be provided to you on the test. So if you go from grams to pounds, I'll tell you that number. Anybody know that number? 454, yeah. 454 grams is 1 pound. Okay. Number of atoms. Okay. There's a couple places that we can pick up, or there's really only one place we can pick up the number of atoms. It's from our formulas. Okay. You'll notice that one of the things I add there is it says it needs to be balanced. Why does it need to be balanced? What does balancing change? Do I need to say that louder, closer to the microphone? When we balance the formula for sodium sulfate, let's come up with a formula for sodium sulfate. What is it? Symbol for sodium.
I'm tired.
I'll back away. Maybe we can avoid recording that. Not because you got it wrong. It was the follow-up. Our formula for sulfate. If this was written as our formula for sodium sulfate, how many sodiums are in sodium sulfate? If this was our formula, we'd say 1. What's the problem with that? It's not 1, it's 2. Why are there 2? You have to make sure your formula is balanced. Sodium has a charge of +1, sulfate has a charge of -2. You need 2 sodiums to balance out the sulfate. So when you're doing conversions on numbers of atoms, you have to make sure that you're using a formula that is correct. If the formula is incorrect, using an incorrect conversion is only going to give you an incorrect answer. Okay. How about the number of molecules? Well, the number of molecules will typically come from balanced equations. With that balanced equation, I can now convert the number of molecules of tin plus 2 ion into the number of molecules of iron plus 2 ion. How do I do that? If I take 1 tin, how many irons do I get? How do I know that? The coefficient from the balanced equation. It allows me to do that conversion. That's why we have the equation. Number of moles. All sorts of different ways you can pull this out. Okay? If you're looking at atoms and molecules, if you're looking at the conversion between atoms and molecules, that's Avogadro's number. 6.022 times 10 to the 23rd, whatever units, is equal to a mole of whatever those units are. Okay? You should have that number memorized. I tend to be of the camp that I think it's kind of a useless thing to memorize because you never use it outside of Gen Chem. Okay? All we're really using that for is to get into moles. Once we're in moles, how can we convert? Formulas and molecules allow us to convert moles of one substance to another substance. Okay? Last part, your conversion factor between mass and moles, or even mass and atoms, is your atomic or molar mass, which comes from the periodic table. Okay? So if we go back through and look at this, what stuff do you have to memorize? It's interesting. All of that information there is given to you except for the metric conversions. Okay? You have to be able to interpret it. But you've already been doing this interpretation. You may be hesitant and think, oh, well, I haven't been doing it. You've been doing it, I promise, guaranteed. All of you have been doing it already. Pick up that confidence that you do already know how to use it. Okay? Another way we could potentially look at it is kind of a straight line system on how we convert from one species to the next, to the next, to the next. Okay? All of these conversions are running through dimensional analysis. Okay? The biggest and probably most frequently used conversion settles right there in the middle. The moles of species A to the moles of species B. That only comes from your balanced reaction equation. Everything else is pretty much gravy on the outsides. Okay? So, let's do another one. What is the molar mass of copper nitrite? It's actually not that careful. You could probably do it pretty sloppily. Copper has a mass of 63. Yeah, okay. 0.55. What's that? I don't want a plus. So we could do AMUs, but then we're asking for the atomic mass unit. What are we asking for? Molar mass. So it's not AMUs. It's going to be grams per mole. Okay, what is the mass of nitrogen?
44.
Stupid 01. Grams per mole. All right, I'll come back to that in a second. Oxygen? 16, officially if we're going to show all that, 16.00 grams per mole. Okay. So if we added those all up, we'd be wrong. What do we have to account for?
The 2.
We have to account that in our formula, this 2 applies to whatever's in front of it, including the nitrogen. So we have to multiply our 14 by 2 to get 28. 28.02. We have to multiply our 16 by Y4. It multiplies O2 by 2, which means I've got 4, which gives me 64. Now what do? Add that number plus that number plus that number, and I get the molar mass for our copper nitrite. 25?
125.5.
All right, that's going to be an important number to write down. 125.55. Did everybody get that number?
155.
Sorry, unanimous decision. 155.55 grams per mole. Why is that going to be an important number to write down? New question. We put down what we wanted as an answer. We put down what we started with. What do we need to do for our conversion? Moles of our copper nitrite need to cancel. So we'll put it in our denominator so it cancels. What needs to show up in the numerator? Grams of our copper nitrite. Is there a conversion factor between the moles and grams? Yeah, what is that? Where does that conversion factor come from? From the periodic table, which you conveniently did on the last question, which we said was 155.57. What number shows up in front of moles? 1. The methodology in this is what's important. The numbers are irrelevant to the calculation. Okay? Questions on that setup? I don't know. What's the answer?
82.7. That's 0.55.
Everybody agree with that? Okay, well, if you guys are getting really nitpicky on that, okay, 7263 is what I heard. And our units would be grams, copper nitrite. And that's exactly what I'm going to do. I'm going to say you're all wrong. That is not the answer.
I got 82.
What is that answer going to be?
82.8.
Your answer needs to be 82.8. Why? You need to account for sig figs. Okay? Because there are only 3 sig figs in our calculation coming from the number given to us.
So on the exam, the correct answer would be
82.8. The odds that I would ask this in a sig fig type fashion where I gave you 82.8 and 82.7526, whatever sequence of numbers, really, really slim. Okay? Mainly because sig figs aren't as important as understanding how to do the calculation. What other answer might show up? I see you.
90.
I would probably go through in the calculator and I would do 0.532 divided by 155. For those of you that said, oh, all you need to do is divide. Did you set the units up right? No? Oh well, look, that number showed up. What other number might I put in there? 155.57 divided by 0.532. Right? And then I would probably make up 2 other answers. Might even write notes. Okay? So it's a question of understanding where you do the calculations. The where comes from the units. Track the units. If you come get help from me, guess what I'm going to want to see? Not just the work, but what about the work? The units of the work. The next issue will be is once I look at your work and I see the units and you're still getting the wrong answer, then what's happening is a calculator mistake. That's a secondary issue. That is one I can help you fix so that you don't make those in the future. Okay? But that is not chemistry related. That is calculation based. Chemistry is in the units. Okay? Questions? Okay, here we go. Oh, shoot. Sorry, I saw your hand.
Questions like that on the test. Sorry about this.
So would I ask the first one, then ask the second one right after it? No. Okay, I wouldn't go through and do that sequence because if you miss the first one, you miss the second one. Okay. What you could potentially see is that first question asked, and then an entirely separate molecule compound asking the second question. Okay, where I might even give you the molecular weight. Okay, to prove that can you do that on top of the extra calculation. Does that make sense? Okay, so new calculation. Atom's mass. What is the mass? In grams of 255 times 10 to the 23rd. I need to stop kicking your backpack. Atoms of lead. Don't shout it out all at once. I'm not going to be able to hear you. Where do you start?
What do you want?
What do you want is your final answer. You weren't asking me what I wanted to do. Just checking.
I can't tell if that's PB or not from this angle.
We want grams. What's our symbol for lead? PB. Guess what question was snuck into this? Nomenclature. Did you remember what the symbol for lead was? Because if you don't know the symbol for lead, can you do this calculation?
Yeah.
Actually, yeah, you could. Okay, you could theoretically do this one. Okay, we'll talk about why in a second. Okay. Actually, no. No, never mind. You couldn't do it with this one. What do we start with? 2.55 times 10 to the 23rd atoms. Okay. Do we have a conversion factor between atoms and grams? There's actually a couple ways we could do this one. No, we do not. What can we convert the atoms to? Anybody? No ideas? Let's convert it to moles. See if that takes us somewhere. If it doesn't take us anywhere, all we did was just waste a little bit of time and go back and we try again. Okay? So can we convert atoms into moles? We can. Good call. How do we do that? I'm hearing the number 6.022 times 10 to the 23rd atoms is equal to what shows up in front of moles? 1. What shows up in front of atoms? 6.022 times 10 to the 23rd. Okay. We now move to the next step of this. We've got moles, and I'd already erased that, but we needed grams of lead. Can I convert moles into grams? Is that possible? Everything's possible. Good call. How is that possible? Where's that conversion found? For those of you shifting your vision away from me, that's actually a good sign. It's found on the periodic table by either side of me. That's why it's good to shift your vision, right? What is that conversion factor? We find lead on the periodic table, which is... You just shouted out the number. There it is. I got you now. 207.2 grams of lead, which is 1 mole. Track the units. What happens with the units? Atoms cancel. Moles cancel. What unit do I have? Grams of lead. There's the final answer. All right, now it's a question of punching it in the calculator, and we got our final answer done. Okay. Rough approximative abilities. What could we potentially do on this? How? 10 to the 23rd in the numerator, 10 to the 23rd in the denominator. What does that mean? Those will cancel each other. 2 divided by 6 is 3. So I've got 1 over 3 times 200. So 200 divided by 3, 60-ish, 70-ish. Within, 50%, it's pretty good. Okay. Coming up with that approximative skill is an important skill that can get you through answers. Okay. So try to simplify that. You should be getting somewhere in that 87 range.